All right, so the setup starts pretty much like this. We'll start with a pseudo-Riemannian manifold, and we have this orthogonal decomposition of its curvature tensor. This wedge product here is something whose specific formula you don't have to know, but in case you saw something similar to this, I'll say this is called the Kulkarni-Nomizu product, and it's essentially a multiplication between twice covariant symmetric tensor fields that output something with the symmetries of a curvature. Now, here we have the rich tensor, the scalar curvature, and the Weyl curvature of M, and our focus will be mainly on the Weyl curvature. Now, a quick review about how you can think about this. So this here, you can think of W as being the remainder of the division of R by G according to this operation. Also, in the case where your manifold is a space-time, you can think of the Weyl tensor as the part of the curvature that's not affected by Einstein's field equations. And from a more computational aspect, what happens is that in dimension n, you have n squared minus 1 over 12 independent Riemann curvature components, but you only have n plus 1 over 2 Ricci components. So the rest has to come from somewhere, and here it is. Okay. One of the important facts about this Weyl tensor is that if the dimension of your manifold is at least equal to 4, which we will assume in this talk, your manifold is conformally flat if and only if the Weyl tensor vanishes. But the condition we'll actually be interested in here is what happens when we have parallel Weyl curvature. Or in other words, what happens, what can you say about your manifold when the obstruction to conformal flatness is a constant? Now, of course, you're interested in a non-zero constant, right? So this brings us to this definition. We'll say that a pseudo-Riemannian manifold is called essentially conformally symmetric, hence the ECS in the title of the talk, if the Weyl curvature is parallel, but your manifold is neither conformally flat or locally symmetric. So we're excluding those trivial cases. Okay? Now, that being said, what is known about this? So the first thing is that those objects, they have strictly indefinite metric signature because of Rotter's theorem from 1977. If you assume that your metric is Riemannian, then parallel Weyl curvature actually implies that your metric is conformally flat or locally symmetric. So this settles the Riemannian case, and then we move on to look at the indefinite case. So other important facts we have about this. So the local structure of such manifolds has been described already by Derzinski and Rotter in 2009. And this local structure is actually better phrased in terms of a certain null parallel distribution your manifold carries. Every ECS manifold has a distinguished null parallel distribution whose rank is always equal to 1 or 2. So we'll refer as the rank of your ECS manifold as being the rank of this distribution. It's always 1 or 2. We'll be focusing on rank 1 today because rank 2 is scary. Let me just put it like this. Okay? And also, since the local structure is known, the next step is to look at global structure. And one of the first things you ask yourself is whether your manifold is compact or not. And it turns out that we do have compact ECS examples of all dimensions. I'm sorry, not all dimensions, just the ones in this form as of 2010, okay? And now those dimensions here are a bit strange, but I will elaborate a little bit more on this, okay? So let me give you an example so you can get some intuition for this. So I'll give you an example of an ECS manifold built from some type of initial data, and the data we fix is like this. You start with a pseudo-Euclidean vector space of dimension at least 2. You take a traceless self-adjoint operator of your space, an open interval in the real line, and you take a smooth function. Then you consider this manifold here. So this here, as the name suggests, is a particular type of a so-called PP wave space-time that pops up in relativity all the time. And by the way, PP wave, this means plane-fronted waves with parallel rays. Okay? So this turns out to have some relationship with physics, and that's at least where I get most of my intuition for this in the rank 1 case. Because the point is, since you have such an explicit formula for the metric, you can compute everything there is to compute about it. And in particular, you can show that this does have parallel Weyl curvature. And moreover, the Weyl tensor is in correspondence with that self-adjoint traceless operator A. And we know that this thing here is going to be locally symmetric if and only if your function f is constant. So provided you avoid those two cases, you have an honest ECS example. Now, that new parallel distribution is actually spanned by the coordinate vector field partial over partial S. And this, the geometric significance of the vector space here is that this thing gets isometrically identified with the space of all parallel sections of D perp mod D. Now, if you're not too used to indefinite metrics, it might seem weird to talk about this here. But the point is that since your distribution consists only of null vectors, this thing here is actually contained in its own orthogonal complement, and the metric survives in the quotient as something non-degenerate. Okay? And moreover, this manifold is complete if and only if the interval we choose here in the beginning is the whole real line, and that's the case we'll be dealing with. Okay? Now, keep this example in mind because this is the central piece of the discussion today. Now, that being said, the 2010 examples, they all have rank 1. And the way they were obtained was by looking for subgroups of the isometry group of that PP wave, acting freely and properly discontinuously as to provide a compact quotient. Now, the thing is, as I mentioned before, those strange dimensions, they turned out to be something very particular to that construction because the way it happened then, they did something and they found such a group gamma in the case where the dimension of V is equal to 3. And then they realized that their construction was compatible with taking Cartesian powers of V. And that's how you get the 3J plus 2. But this particularity was just that. A miracle happens. Okay? You actually get compact ECS manifolds of all dimensions greater or equal to 5. And we'll say not only you have some, you have a lot of them. Okay, so you actually can find an infinite dimensional moduli space of local isometry types of compact rank 1 ECS manifolds. They all turn out to be geodesically complete. They cannot be locally homogeneous. Those examples are not. And as a matter of fact, we suspect that there are no locally homogeneous examples at all. But this is a topic for another day. And by the construction of those ECS manifolds, they turn out to be diffeomorphic to non-trivial torus bundles over the circle. Okay. Now, the plan for the rest of this talk is to give you the gist of the idea how those manifolds are actually constructed. Okay. So the thing is, we fix a period P, and we will look for subgroups of the full isometry group of that model manifold, that PP wave. And we're going to look for subgroups gamma inside of this. So the first thing I have to do is to tell you what this smaller group we'll be doing our search in is. And as a curiosity, the full isometry group turns out to be a semi-direct product between something funny and a Heisenberg group. So there are a few deeper things going on here, but we'll not touch this. Okay? So to first describe GP, we will look at this symplectic vector space of solutions to the second order differential equation that's built from F and A. Morally speaking, this is the killing equation, okay? Because you'll be looking for isometries of that PP wave. And you get this natural symplectic form. You see, this quantity here a priori would depend on T, but the differential equation forces this to be constant. And this is actually a general fact. There's nothing specific about ECS geometry. If you replace F plus A with any self-adjoint operator, you still get a symplectic form. This is called a Morse-Sturm system, if you ever heard of it. And on that space of solutions, we actually have this translation operator that just shifts by P. Okay? So we'll be looking for gamma inside your group GP that's built from this data, and it's actually a product between integers, the real line, and this E, and we have this very specific and explicit formula for the action. The point of me showing those formulas is not like having to remember those formulas. The point I'm trying to make here is that all the calculations can be done explicitly. And the group operation is also given by this formula in terms of this translation operator, okay? Now, what happens next is that if such a subgroup gamma producing a compact quotient exists, it will roughly give rise to a lattice inside a T-invariant first-order subspace of this E omega. Now, the goal here, what we're gonna do, we'll try to reverse engineer the group gamma from the spectrum of that shift operator restricted to L. Now, the thing I haven't told you yet is what is a first-order subspace. And this idea actually turns out to be somewhat simple, and again, it also works for general Morse term systems. And it's pretty much like this. We'll say that it's a vector subspace such that for every T, the map evaluation at T is an isomorphism, okay? And the reason for the name first-order subspace is explained by this correspondence. It turns out that first-order subspaces, according to this definition, they are in correspondence with curves of endomorphisms of V satisfying the certain differential equation. This thing here is just to ensure that your subspaces that you're constructing via this formula actually lie inside of E. Like this differential equation is supposed to play with the previous equation U double dot equals F plus A at U, okay? And from this correspondence and the definition of omega that I'll remind you briefly of, it's just this thing here, you can actually see that those spaces, first order subspaces, which by construction have dimension equal to half of the dimension of E, they turn out to be Lagrangian if and only if each B of T is self-adjoint. Okay? Now, once this is done, this projection onto the first factor, because recall that GP is, as a set, is Z cross R cross E. So this projection is a homomorphism. This restricts to another homomorphism here going out from gamma. And the kernel of this thing will project to a subset which spans a first order subspace. So more or less, this is where the lattice is coming from. And either the subspace that is spanned by this projected image lambda, either is going to be Lagrangian, and this sigma is a lattice here, or lambda itself is a lattice. Now, that being understood, we'll try to go backwards from here. We're going to try to start from something roughly like this and reconstruct gamma. And the way this happens is more or less like this. We have a few steps to choose. So remember, we're going to start from the spectrum of that shift operator restricted to L. So we start with numbers, lambda 1 through lambda sub n minus 2, which will form the spectrum. We assume that they're not equal to 1, and they're not of this form. Like, you don't really want repetitions of those eigenvalues, because the point is we want to build things in such a way that all those operators are diagonalizable, and this is one way to ensure this happens. Now, next, since the dimension is greater or equal to 5, that's one of the assumptions in our theorem, those things are actually realized as the spectrum of an operator of a matrix that actually preserves a certain lattice. So you see, our goal here is to reconstruct gamma, and the first thing we do is to reconstruct sigma. Now, once we got this characteristic polynomial, what do? We use the implicit function theorem, and we obtain an infinite dimensional moduli space of p-periodic functions such that satisfying this equation and another technical condition that will make things work later. And by the way, I would say that in this construction, this is probably the trickiest step, because if you look at the space of C-infinity functions in the circle, that's not a Banach space, right? It's not even Banachable. Like, you cannot get the topology from this from a single norm. And so, like, we want to avoid using things like the Nash-Moser version of the inverse function theorem. So what we had to do here, actually, we applied the implicit function theorem for CK spaces, and then we had a separate technical lemma to recover the regularity, but that's just a fun part of this story. So anyhow, once this is done, we'll let L correspond to this B obtained via the implicit function theorem, via the correspondence between those curves B and first order subspaces. And then the spectrum of the associated shift operator is this thing by construction. And then once this is done, what happens? This subspace L, it will come out Lagrangian also by construction. And the thing is, we will know that the action via left translations, because remember, even though we have as a set Z cross R cross E, the group operation is not a direct product. It also comes from a semi-direct product, as I mentioned in the beginning. But when you restrict to this Lagrangian subspace, because the operation involves omega and omega restricted to L is 0, it does coincide with the vector space operation induced there. So this allows us to use compactness of tori, because if you have a lattice potentially not full inside a vector space, then the quotient is compact if and only if you have a full lattice. So in some sense, compactness of those examples we're going to construct will indirectly follow from compactness of tori. And I'll actually exhibit a compact fundamental domain soon. So the point is, once we have reconstructed sigma with nice properties and this shift operator with the correct spectrum, we define gamma and this works. How does this work? Well, at some point you do have to check that the action of your group gamma is going to be free and properly discontinuous on the PP wave that you built from those initial data. And well, you have an explicit formula for the action, so you do a computation and it follows. Okay? A compact fundamental domain is given by this. It's pretty much like this. You start with a compact fundamental domain for this quotient that produces a tori. You bring it back via this equivariant diffeomorphism between R cross L and R cross V, naturally built from evaluations. And then you just multiply by a closed interval and you're in business. That's pretty much the gist of the conclusion. And last few things to mention is that all the other details that were stated in the theorem, for example, they're like all geodesically complete, they're non-diffeomorphic to non-trivial torus bundle over the circle and things like that, they also follow from this construction if you sit down and pay a little more of attention. So for example, gamma not being virtually a billion, because in this construction we can show that no power of that restricted shift operator can be the identity. This excludes covering of M by tori. Also, what do you know? You know that this map, that's basically the projection onto the first component of your PP wave, and you normalize it by the period, this turns out to be gamma equivariant and induces a fibration, since the fibers are compact. And actually, the fibers, they turn out to be tori as well, because you can just compute this quotient and other things of the sort. Now, the thing here is that some of those features, they're not accidental. We have also shown in another work that if you exclude the locally homogeneous case, because it's actually technically annoying to deal with, and pass into a double covering if needed, every compact rank 1 ECS manifold is diffeomorphic to a bundle over S1, and the leaves of the orthogonal complement of that new parallel distribution I mentioned in the beginning, they appear as the vertical distribution. Now, the story, there's like a lot more of this story, but maybe I'll tell you about it another day. Thank you.
So, do we have questions?
So first of all, thanks for your nice talk. So you have said something about the application of the implicit function theorem. So you say that you are not in a Banach space scenario and you don't want to use Nash-Moser iteration. Can you say which technique you use?
Oh, so, okay, we want to avoid the Nash-Moser version of the implicit function theorem because that's for more general Frechet spaces, but we want to apply the usual version that already we know to hold for Banach spaces. So we applied this implicit function theorem in the space CK of S1. So we actually obtained like CK initial data for the construction. So at this point, we only had compact ECS manifolds of class CK, but we wanted C infinity, and that's how we had this other technical lemma. We basically constructed a smooth preserving retraction of CKS1 to C infinity S1, actually defined on the neighborhood of the fiber of a certain spectrum map.
So
That's
then,
like technical. That's why I didn't want
so
to.
then is it fair to say you used up the classical implicit function theorem? Or?
I mean, we use the classical one.
Okay, so I just, because the way you say it, I had the impression that you invented a machinery that I would love to learn.
Oh, no, 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 no.
Okay, so it's the classical one, and after you use some
Yeah, we use the
regularity-
classical one. The
And
point
after-
is that we didn't want to work with Frechet spaces directly
Yeah,
because it's technical. If,
No, I-
if there's an
I-
easier way to do it, why don't do it, right?
I know a few people want to use Nash Moser. I know,
Yeah.
so especially if you have a way to regularize after you work on
Yes.
classical CK or older space. Okay, thank you.
Are there other questions? I'm not seeing. Shout if I'm blind. In this case, I think we can thank Ivo again. Make yourself comfortable till you have to leave. There's food in the commons room. This is the end of our formal conference.